All right, so I guess just quickly, let's discuss that real quick while I get some of the other stuff loaded here. So, what did we learn about hash tables and hash maps? Did they cover both of those, or just hash tables? Okay, so what are these things? If you were to give me a couple sentence description of what a hash table is and what you might use it for, what would you say? Everybody read, right? And so we could have a quiz on this, right? We would all do well on it. So that means we should all be able to answer this question. Okay, tell me more. Okay, so we're off to a decent start. Storage, yes.
Can easily find where it's pointing to, within one, give it a input and then goes directly to that storage unit.
Okay, so tell me about the hash aspect of it. How does that work?
Modular, give it a key.
Okay, so did the book talk about how it's actually stored under the hood? Did it talk about the applying a hash function to the key you gave? Okay, so what does that mean? What does it mean to apply a hash function? What is a hash function?
Basically takes the key and does something to it.
Give us the
Like
give a what's
the example of it would take it mod usually whatever the size of the hash table was, and then whatever that is where it would look to try and store it.
Okay, so it attempts to give a unique value to your key name. Okay, now what kind of size keys could we have? Give me some examples of the use of a hash table and a key you might use. Okay, student ID could be a last name, could be an age. That might be a little bit less unique, but that kind of stuff, right? So they're words, right? Not necessarily bucket 0, bucket 1, bucket 2. It's bucket foo number. Okay, so now across all the keys that you might ever use for a hash table, what's the range of lengths of those keys? What's the smallest key you could have? 1 character. What's the largest key you could have? A lot of characters? Okay. It's probably something like size of int or size of short, whatever, however strings are implemented or something like that. But a lot of characters. Okay, so we have this giant range of key lengths. Okay. Now you're telling me you're going to pass a key of arbitrary size. Who cares what the size of it is? Through some sort of consistent function, whether it's dealing with modulo stuff or a couple other funny mathy things, whatever it is, and it's going to give you effectively a bucket number, right? A place to put that guy. What's the possible concern with that? So you have you have an infinite number of keys, potentially, right? And each key has an infinite size. Yet you're trying to place it into a finite list of buckets. So the definition of a hash function is it's something that takes an arbitrary size and converts it to a fixed size output. All right? You can think of it like encryption. You can think about it like compression. It doesn't matter how you want to think about it. Okay, but it doesn't matter what the size of the input is for a hash. The output is always a fixed size. All right. So I don't know how Java's implementation is. Maybe they talked about it in the book. Is it maybe the hash function is to produce like a 128-bit key or a 256-bit key? Do they talk about that at all? Okay, I mean, it would be something like that, so they're probably producing, let's just randomly say it's a 128-bit key. So regardless what size hash you give it, what size key you give it, it's going to convert that into 128 bits somehow using a magical hash function. And it's going to always use the same hash function. Otherwise, you can't just randomly choose a hash function because then won't map to the same places than the next time around. You know, every single time you put in the key a certain person's phone number, you want it to get to the same place, right? It's kind of an important aspect of being able to look crap up. All right, but we do have this idea. So let me open up our keynote here. Okay, so if we talk about what a hash function is, we might say converts an arbitrary size input into a fixed size output. Something like that. Doesn't matter what your key looks like, it's going to make it this size on the other end, whatever that size is. So, you know, and keep in mind, this isn't a Java thing. Okay, the idea of a hash function is really it's probably a cryptography or a security thing. All right, so kind of anybody know what this is kind of objective, I guess, but the most famous hash function? They talk about that in the book? Maybe not. We have a famous hash function that I'm pretty sure most of you have seen at some point. A lot of times it's associated with downloading large files from potentially questionable sources to confirm that your what you downloaded is error-free. Something called MD5. Ever seen that before? Seen MD5? The MD5 hash. So you might download a 5 gigabyte movie, all right, and you want to confirm that that movie was correctly downloaded, you know, because you're getting this thing from questionable sources, right? So they might give you the 128-bit MD5 hash of that 5 gigabyte file. So you're turning 5 gigabytes into 128 bits. Now, is that, so here's the computer science trivia question. Is that an example of compression? If you turn 5 gigabytes into 128 bits, is that compression? Typically, when we think about compression, isn't that a two-way street? We should be able to compress down and then decompress back up. Yeah, hash functions are one-way ciphers. So, did the book talk about that? Did it say something like that? Or it's focused more on the Java side of it than the security side of it. Okay, so a hash function in its natural state is a one-way cipher. You don't go back. All right, so we can't go from the hash value back to the original value. That would be awesome if we can turn 128 bits back into 5 gigabytes. Okay, but it kind of defies the laws of logic or something to take any size input and make it a fixed size output. Because what you have then, we have the risk of collisions. Did I talk about that? Okay. Okay. See, I did my homework. I read the book, clearly. Well, at least I kind of knew what these were. So you have this risk of collisions, which means you might have two keys that to a human look completely different, but they might hash to the same value. It's a risk. So most implementations of hash tables, let's say, they have built into it kind of a secondary approach to collision, either avoidance or collision, I guess, handling. Okay, for Java's hash tables, collision avoidance isn't going to help them, because if you put something in with a key, you're expecting it to actually store, right? So, you know, it's not really acceptable for Java to come back and say, yeah, we tried, but no. Okay, this other foo number just happened to map to the same value. I mean, think about it in a worst case scenario. Let's say you were hashing your foo numbers into 2-bit numbers. Okay, so we have a whole bunch of people in here, and with 2 bits, we can represent 4 different, not a lot, right? We will have collisions, okay? Absolutely we'll have collisions, and we can just take it, you know, you can add up all of the Unicode values in your food number, let's say, and then you can mod it by 4 and convert that to binary. And you will have more than one person with a 0, more than one person with a 1, and it will happen. Okay, that would be a collision. Well, in Java, we wouldn't say it's acceptable that we can store information for you, but not for you. Sorry, bad luck, bad food number, or bad order adding the food numbers. Okay, so Java is going to have a secondary means by which to handle this. Did they talk about how they did that? Okay, how?
Well, I guess they talked about a couple different ways of doing it, but one of the ones that they talked about was like the idea of chaining, where each index in like the array or whatever they're storing it is actually a list.
Yeah, so now what we're marrying, we have this hash table, and each bucket of our hash table, so let's say if we have a 128-bit value, that means we have, if that were the case, that means well, here's a mathy question. If you are hashing to 128 bits, what's the maximum number of elements you can store? If your fixed size output is 128 bits, how many unique 128-bit numbers are there? So this is what happens when we have a math requirement that only makes you take introduction to numbers. This week, class, we are dealing with the number 7. Like Sesame Street, right? And the letter C. How many of you still watch Sesame Street? Oscar the Grouch is not on as much as he used to be. I'm disappointed by this. You know what I'm talking about. Oscar was wasn't it funny? He was every kid's favorite, but he wasn't supposed to be, right? We just loved that guy. What happened, though, as I got older, he became nicer. Yeah. He's probably had parents complaining, like, we can't have the mean, dirty guy coming out of the garbage can. It's got to be nicer to the kids. Stop watching it then. I will start watching it again now because, Mr. Gonzalez and all that. All right, so usage. So the question was how many unique values can we store in a hash table whose hash values are 128 bits? So it would be 2 to the 128th power. A lot. All right, so I think we can do that in here, right? 2 to the 128, that number. If we happen to choose 128-bit keys. Okay, that's the number of unique values that we can have. That's the number of unique 128-bit values that exist. Now, we're not guaranteed that every key will hash to one of those unique, well, it'll hash to one of those unique values, but we're not guaranteed that 2 keys won't hash to the same value, and that's where these collisions come in. Okay, so Java's approach to this is, hey, why don't we, at every bucket of this hash table, why don't we go ahead and just put a linked list there? Okay, and if we have more than one thing that ultimately hashes to the same value, rather than screaming at the user saying, sorry, okay, if these 2 foo numbers both hash to the same value and we put him in first, he'll be at bucket 0 of that linked list and he'll be at bucket 1 of that linked list. So with a hash value, what we'll end up doing is we'll get to the right neighborhood and then we can search within that linked list. All right, so it kind of gets us close. All right, so that's the idea of a hash function. What's good about hash functions? Why would you use them? Seems like there's all we've talked about so far is maybe problems. What's good about these guys? Okay, faster for searching because it lets us dig into the neighborhood, like I kind of put it. For where something is, and then from there, if we happen to have a linked list, at least we're dealing with a much smaller set of values. Okay, faster for searching, certainly. Anything else? What about convenience for the programmer? If I want to look up Corey's record, wouldn't it be convenient for me to take my hash map and look at bucket, whatever your foo number is? It's probably a piece of information I have readily available to me, right? It's kind of convenient, right? In some other languages, these are called dictionaries. In older languages, before they called them things that meant something to humans, I guess, well, I don't know, I guess this sort of means something. In an old language like Perl, they were called, anybody know what this kind of animal was called in Perl? I mean, because it kind of is like an array, right? It's an array, but instead of numerically numbering our buckets, bucket 0, 1, 2, 3, we're, naming them cat, dog, elephant, whatever. You have words, okay? So in Perl, these were called associative arrays. So it was an array, but instead of an index, it had you had an association. This word maps to the value that's at that word. Okay, pretty popular data structure actually in modern programming, regardless of the performance benefits under the hood. Forget about it, because with those performance benefits, the faster searching does come some headaches that have to be dealt with, right? Okay, so in Java, it's pretty easy to work with because they just throw a linked list there and say, I mean, fine, this will be a slow search on this linked list, but there's only 8 things in it instead of the 4 zillion things you're storing. Not the end of the world. So we can say performance really isn't an issue. But then you have to look at what's the performance of your hash function. Now, with Java being, let's call it collision accepting, I guess, because a lot of times these different, like MD5 is famous for collision avoidance. So they take steps to make it more unlikely for collisions to occur. Java doesn't do that. But now with MD5, with those additional steps to be taken for collisions to not occur, means that hashing function is kind of a monster, right? It's a very mathy, multiple passes through this thing deal where applying that hash takes a lot of computational time. Might not be time a human being notices. I mean, if you do an MD5 on a 5 gigabyte file, it'll come back to you pretty quick because it's all just number crunching. All right, so it's not like it's, I have to wait 15 minutes to find out if my 8-minute download was correct. So I might as well just download it again if it doesn't work, right? So it's faster than that. But with Java, they said, look, if collisions happen, they happen. We have a backup plan. Just throw it in a linked list there, no harm, no foul. All right, so what does that likely tell us about the hash function that Java's implementation of a hash table must use? Do you think it's probably a very complex, highly advanced hash function similar to MD5? Or do you think it's probably as simple of a hash function that I could have come up with? Or something closer to that side of things? Probably a simple hash function, since they didn't have to worry about mathematically making collisions unlikely. They could just say, look, they're going to happen. We'll deal. Okay? So the hash function is probably something very simple. Did they actually talk about what the hash function is? I heard you say something about modulus. Did they advertise how the hash function specifically works, or they just do something with modulus?
We just talked about it.
All right, so they're doing some mathy stuff to your key and coming up with fixed size output. All right, and that's fine. So there's some performance benefits, but I think the bigger deal for us as programmers is there's convenience benefits. We like storing things in, we like words, not numbers. It's very impersonal to say, I want this array at bucket 7. We could say, oh, that's some person. Well, if I say I want this hash map at bucket your foo number, now I know it's specifically the person Corey. That makes sense? All right, so it kind of gives us that kind of convenience. Now, interestingly, if we kind of finish connecting the dots with the history of this stuff, what's the difference? And maybe a hash map kind of takes this to the final step. But if you think back to when we first introduced like the difference between our older languages like C to C++, we talked about in C, we kept, C had something called structs, right? Structs were essentially a collection of name-value pairs. Doesn't that kind of sound like a hash table? collection of name value pairs. You put 3 or 4 keys in, they have values associated with it. Here's a name value pair, here's another name value pair, it's another name value pair. And those pairs didn't have to be the same value types. So hash tables hold objects. Okay? You could tell them to hold a specific kind of object if you want, but you could have it hold a string for first name, a string for last name, a number for age, that kind of stuff. Okay? So these are kind of almost a throwback to something from a long, long, long time ago. So C had structs, C++, but they didn't have objects. What's an object relative to a struct? Remember, we talked about this. We drew, this was probably 200 stuff, right? So when we first introduced what are programming languages and we talked about the history of these guys, a struct has a bunch of name value pairs, but doesn't have functions associated with it. So these objects we've gotten used to, they can do things, right? So objects can actually accomplish stuff, but a dictionary really can't. A hash map really can't. It can just store data. And that's okay, because a lot of times that's all we want to do is store data, correct? I mean, there's nothing wrong with just storing data, so if it's the right tool for the job. But when we use objects is when we want our data that's being stored to maybe do something extra, right? And we talked about how Java kind of erroneously got rid of structs. So Java said, hey, isn't a object that has no methods the same thing as a struct? If we say that a struct that's going to hold a first name, a last name, and an age, isn't that actually the same thing as a person class where I have 3 fields, first name, last name, and age, but just choose not to write any methods? Aren't they the same thing? On the surface, it seems like it, but what did we talk about as the difference between structs and objects? It's something that's only going to bite us every now and then, but when it does, it might be one of those bugs that's hard to trace down. So this gets back to that idea of pass by value versus pass by reference, right? Whether something has side effect. By default, structs are passed by value. Objects, by default, are passed by reference, by address. That means if you pass a struct to something and you internally change the value of that struct, externally, there was no side effect. It had no impact on the global variable because what was passed to it was a copy of that structure. Whereas if you pass an object to something, you can change that object and it does have side effect. It had global consequences because you passed it by reference. You told it where it can find that object in memory. Now, in a language like C++, we don't have to rely on the defaults. We can say, I'm going to pass this struct by reference. You put the little ampersand before it and say, here's the address of the struct. Have fun. And then, now you've short-circuited the idea of how it works by default. But when you move to these more modern languages, for instance, like Java, Java's taken away that syntax. We don't have a means to say, oh, I want this guy to be passed by address, and I want this guy to be passed by value. Okay. So interesting. I guess another trivia thing. I don't think this is something I've actually covered in class, but we'll talk about it right now. Let's say that you have a function that you want to pass an object to. So let's say I get a person object. Okay. I get a person object from we'll just keep it with our hash table thing. This question has nothing to do with the hash table thing. So I've extracted the person object associated with Corey. Okay. Now I want to pass that guy into a function, and I want that function to manipulate that object, but I do not want it to have global consequences. So I want to pass an object to a function by value, or so that it acts like it was passed by value. How do you do that in Java? Or, let me ask it, let's ask it 2 different ways. I'm telling you there's a built-in way to do this in Java. If you don't know what the built-in way is, which I haven't introduced, so you would only know it if you've dealt with this out externally, how would you accomplish that? Let's say I gave you a homework assignment that said, here's an object, have it get passed to this function, have the function change it, have it not have global consequences, not have side effects. How would you accomplish that? So that inside the function you have all the data that was in that object, but you knew that changes were local only changes. They were not permanent.
Put it into a temp or something.
Okay, tell me about how you're going to put it into that temp.
Well, I don't know if it works kind of like a list array.
So we're going to say it's a person object. It's a person object.
Get the string or whatever it's associated with.
Oh, okay. So if I want to change
Get
the,
data itself out of it.
so you'll extract the data into individual variables, and as long as that data isn't an object type,
Right.
right? Because if we had a classroom object that had a list of or an array of people in it, and I extracted one of those people, even if I put that in a temporary variable, that's still a pointer. Okay, because that's an object. But if it was a string or an int, something like that, yeah, that would work. But I want to kind of protect the person inside the function. So whoever's using this function, I want to say, look, here is an object that you don't have to worry about. Whatever you, or actually it's really the other way around. Okay, I'm passing somebody an object to work with, but I'm going to have the knowledge that anything that they might do won't break the original object. Okay, so I'm gonna this is human trafficking at its best. Okay, so we're gonna pass Corey off to a function, but in such a way that anything that they do to Corey in that function, okay, doesn't impact the real deal. It's actually funny because the real answer in Java was what you might guess is the answer. But in any case, how would you pull this off, knowing only what you know right now? And if you already know how Java automates this, don't answer yet. Don't necessarily overthink it. Let's think about what is the Corey object. We're going to keep it simple, maybe a first name, last name, and an age. Okay, I mean, you're really no more complex than that. That's it. I mean, maybe a height, but that's not impressive. So it's all right. So first name. I mean, he's got height, right? You're 6'4", maybe.
I don't know, 6'2".
6'2". Yeah, I mean, he's taller than you. Any way you cut it. Yeah, most people are. So. All right. So in any case, we're gonna take. So he has functions. He has things that he can accomplish, right? Okay. But at the end of the day, the stuff we're really thinking about protecting are the fields, right? The data associated with them. So his first name, his last name, his age. Couldn't we go ahead and just create a brand new person object and pass into the constructor, assuming the constructor takes first name, last name, and age, pass in his first name, his last name, his age, build a brand new object. We have two Corys sitting right next to each other. We can't tell the difference other than we know this other one is new and might still hit their growth spurt. So
I think that's what isn't that what you were trying to
That's what I was going for.
That's why I didn't give that answer, is because
I was going for
He was
just
going for
copying
it,
it
so,
to
yeah.
a whole new object.
okay, and which is fine. That's why I did say kind of explain more, but that's fine. Yeah. Okay, so we can do that. Now we have two separate objects that live in two different places in memory that happen to have the same fields. Now, we do need to be careful though, because if let's say Corey had a list of pets, and that came with the person object. Okay, and each of those pets is an object itself. You're going to have to make copies of the pets too as they come out. Because those would end up being pointers. So then if I pass it in thinking that I'm free and clear, and somebody changes one of Corey's pets, Corey's going to get home and somebody spray painted the poodle. I think people do that, don't people put non-toxic paint on their dogs to make them look? That's the thing, right? You say you've seen it, I've done it. He's got a startup in his garage. Except he only works with dangerous breeds, and he uses only finger painting. Oh. Oh my gosh. My wife the other day said she wants to get cats again. And I said, no, we're done with cats. We had cats for 14 years, and now I can travel wherever I want and I have to worry about leaving cats at home. So I gave her a list of pets she's allowed to have. Bengal tiger, bear, alligator, any form of lizard, because that would be funny based on the situation in Florida. But yeah, she decided that she didn't need a pet. I say, don't you have Mr. Gonzalez? He does have a pet. Oh yeah, I have a picture. Mr. Gonzalez has a pet baby seal. His name is Ziki. It's a white seal, so it's actually tzatziki, that sauce, that white sauce, but he just calls him Ziki. Yeah, the story goes deep. It would be really difficult for you to to get to something that actually becomes unreasonable. All right, so we can certainly build our own secondary object and make sure any objects that were within it were also secondary objects. That way we know that they have the same content, but they live in different places in memory. Okay, now Java has a built-in function that does accomplish this. Does anybody know what that is? Okay, there's a clone function in Java. You do need to be careful with it though. And that comes down to that secondary list of stuff. Okay, now I'm pretty sure starting in Java 8 that the clone function does take care of those secondary objects. It handles any sub-objects within an object. What it used to not do is it wouldn't make clones of things that were in lists. I think it does now, but I'm going to say 84% certain. Okay. But at the very least, for simple objects, we can tell Java to clone something, and what it does is it actually clones the memory. So instead of it actually building a brand new object, it says, okay, I'm going to go where this object lives, and then I'm going to request some new memory over here. I'll just copy all that over here. So now you have two separate pointers. That make sense? Now, this isn't something that you're necessarily going to have to use that often, okay? But it might come in handy for something like cloning a health potion, okay? So it's something him and I had talked about the other day for a game he's working on. So things like that, where you want to hand them a copy of the thing and don't want to have to do that much work but that's not really any different than just creating a new instance of your potion, okay? So some things to discuss there with hash functions, I guess. All right, questions about any of that? Now, would this guy be all that difficult to write? I mean, isn't it effectively maybe a linked list with a linked list inside of it? Maybe the tougher aspect of it would be the hashing. You know, kind of going to a bucket associated with this hash, but you'd probably have a array that had a mapping table that this key maps to this bucket, something like that, for how you'd actually implement it. But at the end of the day, if I had asked you to implement a hash table, this wouldn't be like a ridiculous assignment. It would kind of be similar to almost like what we're working on right now with the shunting yard, where we're kind of using some data structures we've already been introduced to together to solve a larger problem, right? Okay, so having said that, let's go back to our shunting yard and finish that guy up. All right, and where did we leave off? Well, of course, there's another update. Okay, so shunting yard, currently when we build our shunting yard, we're passing in all of our views, right? Good. So we hook all that crap up. When we do process expression, we clear out all of our data structures. So we have a bunch of empty stacks and queues to work with. Then we go ahead and tokenize whatever's in our input text currently. on that plus minus times divide. Okay. We currently are not handling spaces. We could, as we get each token, tell it to trim itself, and that would get rid of spaces. So, because I think what we had assumed is you would have no spaces in your string, right? I think you had assumed you had to have spaces in your string because you tokenized on spaces, right? So one thing we could do is if we wanted to tokenize on those operators and keep the operators as our tokens coming back, but we wanted to give the end user the flexibility of either putting spaces in or not putting spaces in. All we would have to change here is when we get our next token, we would go ahead and just tell that token to trim itself. Okay. Have we looked at the trim function before? I think we have. Have it? Okay. So what trim does is it takes a string and it removes all leading spaces and all trailing spaces. It doesn't touch spaces in the middle. So hello, 5 spaces, hello space world, 4 spaces would turn into hello space world only. So it won't remove spaces in the middle of the word, but it gets rid of, it trims, right? Trims the beginning and the end of a word or of a string, gets all those spaces off. All right, so what we're doing here is now we're allowing our user to put spaces between their numbers and their operators that they want. And if you had 127 space plus, when you tokenize that, the first token be 127 space. And we'll just cut the space off with a trim and give us the 127. If there's nothing to trim, trim just returns the original. Make sense? So pretty easy fix to now allow spaces for that guy. Okay, so now as long as our user puts in things that are numbers and things that are legal operators, it'll work with it fine. It doesn't matter whether they put spaces in there or not. Okay, so notice that, remember, we have our, when we get the next token, that burns it off of our tokenizer. It's kind of like popping it off the stack. So I stored in a temporary variable. I could have on the next line said text equals text.trim if I would have rather written it that way. Otherwise, this will boil down to that token. I'll go ahead and trim that token, and I'll store the result inside of text. Then I added text to my input queue, but I also created a text view for this guy. And this context, when you create a text view, you need the context in which you're creating it. So I'm pretty sure the context is, acceptable context is an activity. So I went ahead and I passed in, remember from last time, our original activity. So this is main activity we passed in there. That way we would have a context in which to build our objects. You might actually be able to request from Android the default context. I think that might be a possibility thing, but whatever. I mean, we just passed in the context so we can use it. Okay, so I'm going to build a brand new text view. It's effectively a label, right? Using this context that kind of allows you to build it, and it built the frame in the right place. And then I'm going to set the text to that guy to the same thing that we had in that token, right? Because so we held the token inside of text, and we used that variable twice. We used it to add it to our queue. We also used it to add the text here. Then we go ahead and we added that label, that text view, to our input queue. Okay, and our input queue should be a horizontal linear layout. And I believe that adding always adds to the end. I guess we're going to find that out here in a moment. If it doesn't, we'll have to do some indexing. But so that's assuming what happens here, right? All right, so when we call process expression, it should read that in, it should tokenize it, it should add this stuff to our input queue, which is our behind the scenes data structure. And then it should also have our horizontal linear layout filled up with labels that have the values in them. Okay, so let's just test that, just that piece of it. So back here in main activity, we went ahead and we created our shunting yard, which we had as a global variable up here. We passed it all of our, linear layouts and stuff like that. And we also passed it this, which is this instance of main activity. This was our context that we passed them. Okay, and then when they click the process button pressed button, we're going to go ahead and tell that shunting yard to process that expression, which should load up our data structures and then also make our input queue have the labels in it. Okay, so let's see if we have introduced any bugs in there. Just real quick, let's make sure we have our button hooked up with its on click. It was definitely hooked up at some point. Okay, it looks like it's hooked up, so we'll test this guy. Okay, so we'll do 127 plus 8 minus 4, something like that. We'll call parse expression, and we get 127 plus 8 minus 4. All right, and those guys are actual labels that have stuff in them. We can prove that if we want to put little smiley faces in our as we add this thing to the label, we can concatenate onto that a smiley face. (127 minus 2 plus 4), and now you see we have smiley faces in there. All right, so this is a label right here. This is another label right here. This is another label right here. This is another label right here. Okay? So let's take our smiley faces off so we don't accidentally try to do math with those. All right, so now that's what happens when we say parse expression. Now we want to go ahead and process that expression. Okay, and what does processing that expression mean? It means, here's our process input queue. Okay, so as long as we have something in our input queue, if we don't, we'll just return false from this guy. We go ahead and we dequeue thing that's currently there. All right, we ask whether or not it's an operator. If it's not an operator, that means it equals -1. The easy mode is we add this to our output queue. Okay, but now we also need to go ahead and move that label from our input queue to our output queue. Make sense? Okay, so inside here we need to add something to our output queue that came from our input queue. So let's say this dot output queue view dot add view. The view we're going to add is this dot input queue view dot remove. Oh, I remember it's a two-step process, right? So we're going to say should we just say Textview temp is equal to this dot input queue view dot get, so get child, yeah, get child at index, and we'll get index 0. Then we'll go ahead and say this dot input queue view dot remove view at 0. So we preserved it. Oh, we can't do that in temp. Let's just call this temp view. And in actuality, we'll just treat this as a generic view. We're not doing anything with it. So it's going to come out as a generic view, we know it's a text view, but we're not changing it at all, so we don't need to have access to the text view functions. So we don't need to remind Java that this guy is actually a text view so we can set text and anything, because we're just moving it from one place to another, and we can just use the view pointer. It's fine. Okay, so this adds temp to our data structure queue. This retrieves the first element from our visible queue, okay, our linear layout. This then removes it from our input queue linear layout. Then this will add it to our linear layout. That is our output queue. All right, so that's what we do when we are moving a non-operator. When we're moving an operator, I'm going to go ahead and steal these 3 lines here. We check, is the op stack empty? If it is, we're allowed to just go ahead and add this guy. Okay. Now the op stack, we're always going to add at bucket 0. Okay, because we're pushing it onto the op stack. So we'll go ahead and we'll get the view from our input view at bucket 0. We'll remove it from the input queue. Then we're going to go ahead and add. So we're going to say this dot op stack view dot add view. Isn't there a yeah, there it goes. Add view at index. Okay. So the view we're going to add is temp view, and the index we're going to add it is 0. That way we're always pushing onto the top of the stack rather than letting the add function add it to the end, which it would do naturally. Okay, so this is what we'll do when we add a operator. Now, this is the trivial added operator function, right? There's nothing on the op stack. I don't need to do any special checking. There's your operator. So we do it, we make it true in the data structure behind the scenes, then we make it true visually on the screen. Make sense, the difference here? So this is almost like if we go back to when we talked about like a parallel array implementation of things, where we have 2 different arrays where bucket 0 of this guy is the same as is related to bucket 0 of this guy. We have a similar type of problem solving approach here where we have data structures behind the scenes here like opstack, and that guy is related to opstack view. This is the visual aspect of our opstack. This is the data structure version of our opstack that allows us to actually do stuff, logic stuff. That make sense? Okay. Otherwise, this is when we go ahead and we enqueue things from our op stack. Finally, when we push onto our op stack here, which is the same thing we did here, we'll do that same stuff. But we also need to, when we get something off of our op stack, we need to go ahead and remove it from our op stack. So this is when we enqueue something from the op stack pop. So we got to remove from op stack. We always remove from position 0. Okay? So we'll say view temp view is equal to this dot op stack view dot get child at 0. This dot op stack view dot remove view at 0. And then we'll say this dot output queue view dot add view, and we'll let it do the natural add to the end of the line, which is going to be our temp view. That make sense? So this removes the view from the top of the op stack view. Well, this gets the view from the top of the op stack view. This actually removes the view from the top of the op stack view. This adds that view we removed to the end of the output queue view. Make sense? So see how we're having to use those linear layouts, kind of, we're treating them like they're either stacks or queues. by doing the right adds and removes from the right places. Okay. So every single time we pop something off our op stack, we'll also remove something from the top of the op stack view and put it onto the end of the output queue view. Okay. Then we have our, we finally are allowed to push our operator onto the op stack. That make sense? All right. So this is process input queue. This makes exactly one move on our input queue. Takes the front of the input queue and says, what should I do with this guy? And it makes all the necessary moves. Okay, so let's go ahead and hook this guy up to a button so we can kind of step through shunting yard up to, but not including the actual math version of it, right? Okay, oh, I need to go to my interface here. So we're going to give ourselves another button here. Ruh-roh. I didn't put it where I wanted it. Oh, that's because I'm choosing buttons that already exist here. I'm grabbing buttons from bad places is what I'm doing. There we go. Nailed it. Yeah, these are buttons that are already on our interface. These are first time in the interface builder. Okay. And we'll call this guy process. Actually, let's call this guy step input queue. And then on click, oh, we need to go ahead and give ourselves a action for this dude. So that'll be inside of our activity. It'll be pretty similar to this guy. So this would be a public void step input queue button pressed. All right, and we'll go ahead and say what is it? Process input queue. Oh, there it is. All right, so that's what we want that guy to do. We want it to process our input queue, and this just does one element. So we're going to have to hit this button multiple times to see stuff dance around. Okay. Now we need to go and hook it up to, where are we at here? This guy. Is it going to work? I guess let's find out. I did update this the other day, so it's possible. Like, you would just keep hoping that up. I mean, all of you are running into a similar thing when you're doing your code, right? That yours always works? Really? This has been like this for years. Well, actually not for years. This has been like this for a year. Before that, it wasn't even an option to choose. You just got to. So it always worked when you just paste the stuff in there. Do you paste or use the drop down?
Use the drop down.
You know, I bet it is. Actually, wouldn't it be hilarious if this was it? She's using Emma syntax with the curly brace at the end of the. I mean, there is at least a small chance that is the case. It's legitimately a possibility, given the way it's probably parsing that code. That would be really funny. All right, 127 minus 2 times 8, something like that. All right, so we'll go ahead and we'll parse that expression first. We probably would have this button, not clickable until we've already parsed the expression, but whatever. So we'll parse that expression so we see our input queue looks legit. Now, when we step our input queue, this 127 is going to come off. Where do we expect that to go? We expect that to go on our output queue. So there it is, on our output queue. All right. Now, the minus comes off. Where do we expect the minus to go? Op stack. So there it is in our op stack. The 2 comes off. Where do we expect that to go? Output queue. All right. Yeah, these kind of ugly looking here. We probably want to add some padding in there, but we'll get there. All right. Multiplication comes off. Where does that go? It's ultimately going to go on our op stack. But should anything happen to the minus first? Multiplication is greater than minus, so we're allowed to just push it right on top, right? Did we do that? We didn't do that. We didn't do that. We got to go check our logic. Our logic's not doing doing good stuff. So it did stuff, but it did the wrong stuff. So let's go look at our shunting yard. So this was the is empty thing, and we clearly were not doing that because we did some popping. All right, so we went ahead and got the value for our op. We passed it temp. All right, so in this case, that would be the value for op multiplication. And let's just take a peek at value for op. So op should be multiplication. It should return a 1 in this case. All right, so if value for op of multiplication, if our stack is not empty and the value for op stack peak is less than or equal to 1. Oh, we have this backwards. This should be greater than or equal to. Because this says, when should we pop from this stack? We should pop from this stack when the top of the stack is currently greater than or equal to the guy we're trying to put onto the stack. All right? So I tested you last class. You all failed. 100% of you. Anybody skip last class? You didn't fail. Well, you did fail, but for other reasons. Other reasons. All right, all right, let's try this again. Should be good now. See, sometimes I introduce little logic issues like that in, and so try to keep you on your toes. But I see Bakari back there. He's usually searching the Walgreens catalog for fabric softener sales. What's this? Well, he said he likes the liquid, right? Instead of the sheets. I have to start having my my wife's laundry go through some sort of quality control. I keep finding those sheets in my clothes or in the bed. She says my clothes are too big; they get lost in there. This is an excuse. What was I doing? Okay. 127 minus 2 times 8, parse expression, step, step, step. All right, so now we should see the multiplication go directly on top of the subtraction, and it does. Okay, so now it's doing what it should do. Then we have the 8. 8 should go to our output queue, step. All right, so now if we step again, it shouldn't do anything, right? We're out of stuff to step. All right, but now what's the next thing that should happen? The next thing that should happen is we need to clear our op stack. Correct? Okay, so the op stack could go ahead and get cleared. So one thing we could do here is as part of our step input queue, we could go ahead and say, we'll just add a little logic in there that says if the op stack has stuff in it, go ahead and pop that off so we see those last moves. All right. So right here, we're returning false instead of returning true. What we're going to go ahead and do here, though, is before we return false, let's ask the question, is there something on our op stack? Okay, so if this dot op stack dot is empty equal to false or not equal to true. So if that guy is not empty, then we want to go ahead and do the move from OpStack stuff, which we find right here. Right? That's the logic we use when we pop something off the OpStack and put it onto our output queue. So we'll go ahead and do that. We'll still return false here. I'm not sure how we're going to use that Boolean yet, maybe whether or not we needed to do stuff. But actually, you know what? We probably want to return true here because we did do something that was necessary. We want to return false here when literally there is nothing else to do. That make sense? Because even though we have nothing to process from the input queue, if we still have to clear that OpStack, we want this guy to keep getting called. Because think about this, we're probably going to have the process input queue inside of a loop somewhere. Keep going until this guy returns false. So it does all those steps automagically. Okay. So let's run this guy again and make sure it also then clears our Okay, so now we've cleared our input queue. When we step again, we see our OpStack pop. OpStack pop. Now it should do nothing. Okay, finally, we want to perform math, right? Okay, so we'll have another button that's ultimately going to perform math. And what does perform math do? Perform math pops from, actually it doesn't pop. It removes from our input queue if it is, and it removes from the front, right? This is a queue, not a stack. So queues, we remove from the front, we add to the end. So this will remove from the front. If it's a number, what do we do with it? Put it on the solution stack. Okay. If it's an operator, what do we do with it? No, that's if we're working off the input queue. Right now we're working off our output queue. So we're in the middle of doing math now, right? So when I read in this 127, I'm going to go ahead and push it onto the solution stack. Then I'm going to read in the 2. I'll push that onto the solution stack. Then I'm going to read in the multiplication. When we read in an operator, it says, do some math. Doing some math requires 2 things, right? The 2 things that are currently on our solution stack. So we'll pop off our solution stack twice, perform the math operation, push the result back onto our solution stack. Make sense? All right, so let's go ahead and do these moves. So we'll call this guy public Boolean process output queue. Okay, so as long as there's stuff in our output queue, we want to go ahead and process that stuff. All right, so if this dot output queue dot, this is our queue that we wrote, so we have to get the count. If the count is not equal to 0, we're going to do some stuff, right? If it is equal to 0, that means we're done. That means the answer should be sitting there for us to see on the solution stack. All right, so we're going to go ahead and pop the first thing off of this queue. So we're going to go ahead and say things that are coming off this are always strings, correct? So we'll say string temp is equal to this dot output queue dot dequeue. We'll go ahead and remove that guy off of there. Now, at the same time, we know we're going to be doing something with the view of this guy. So let's go ahead and get the view as well. Okay. So string temp view, I'm sorry, string view temp view is equal to this dot output Q view dot get child at index 0. Then go ahead and say this dot output Q view dot remove at 0. All right, so now we've visually taken it off the output queue. We've actually taken it off the output queue. We have those two guys stored in variables. Okay? Then we ask the question, if it is a number, then we do something with it. Okay? Probably the easier way to ask is if it's not a operator. Okay? And we've asked that question before, so we'll ask if plus minus times divide dot index of temp is equal to -1. That means we are looking at a number, right? So we have temp. We say, if I look for this value inside of plus minus times divide and I don't find it, he's a number. Or we put in illegal input, which we're not testing for. So he's a number. What do I do with that number? With numbers, I push it onto the solution stack, right? So we'll go ahead and say this dot solution stack dot push temp. We'll also say this dot solution stack view dot add view at index. And the view we're going to add is temp view, and the index is 0. Okay? So that's the move we make when we are dealing with something that is not an operator. Else, we are looking at an operator, time to do math. All right? And to do math, what do? We have to get the two top numbers from our our solution stack should definitely have two things on it, right? So we need to get the two numbers off our solution stack. So, and we get them it's in reverse order, right? So we're going to get num2, then we're going to get num1. So we'll say string num1. Actually, let's go ahead and get them as integers right now. Okay, so we'll say int num1 is equal to this dot, and I'm lying, I just said num2. So this dot solution stack dot pop, that's going to give me a string. And what do I want to do with that string? I want to say integer dot parse int of that string so I get that number. Okay, we'll do the same thing for num2. Or for num1, I'm sorry. Okay, now we already have our operator stored here in temp. Oh, dq.get payload. That's our string. You dying?
Maybe.
I know the Heimlich. Actually, at my church, we did the CPR training or whatever. I broke the baby.
My second grade teacher didn't give me that one.
Really?
Yeah. Broken my kid. No.
It totally happened to me too when I was a kid. I tried to take a big old piece because they were trying to catch me and trying to take it away from me. So I had to eat the whole thing real quick. True story. All right. So we have our, if it's a number, just push it onto the solution stack. Otherwise, get our two numbers, decide which operator we're dealing with. If temp dot equals plus, we'll do addition. Else, if temp dot equals subtraction, multiplication, division. Okay, so we have num1 and num2. So we'll add num1 and num2, and we'll push the result back onto the stack. Now, we can go ahead and just burn the numbers from our solution stack, correct? We don't need to store them anywhere because we're not going to be putting them back. We're going to be putting a brand new number onto the solution stack. So we'll go ahead and say this dot solution stack view dot remove view at 0, and we'll do that twice. We're not going to store it. We're just going to let those couple of labels die. Okay? Then we're going to go ahead and we'll do our math. So we'll say, actually, let's go ahead and give us our a text view real quick. So we'll say text view TV is equal to a new text view, this dot context. And we'll say TV dot set text to the empty string concatenated with num1 plus num2. And then we'll say this dot solution stack. Actually, let's do this real quick. String answer is equal to that. So then we'll set the text to answer. We'll push onto our solution stack the answer. And then we'll also say TV, or we'll say this dot solution stack view dot add view. What view? TV at index 0. We'll do the same thing for the other mathy things. We'll just change the mathy thing. It's minus. That's times. That's divide. Okay. So that's our process output queue. So we're going to associate that with a button that should do all the popping and all that stuff. So we'll do that right at the beginning of class last time just to see it. I'm pretty sure it works as it is right now. Let me bring the book up real quick. So I want you to start reading about trees. Okay, so let's read 4.1 through 4.7. So not AVL trees. So stop before AVL trees. Make sense? 4.1 to 4.7 for Tuesday. We will have an assignment on Tuesday, due Thursday. For those of you, I haven't decided if I'm going to give a homework assignment I'll probably give a homework assignment over the weekend, but if you're doing the hackathon, you'll be excused from it so that everybody's doing some sort of programming over the weekend. All right? So I guess be prepared for that. Okay, I will see everybody on Tuesday. Remember, if you are going to do the hackathon, which I would strongly encourage all of you to do, make sure you email Professor Josh Locklear today, soon as possible, letting him know that you will be there for the hackathon from 8 a.m. to 8 p.m. on Saturday the 8th. That's a week from this coming Saturday. And if you're interested in the boot camp on Tuesday night in this room from 6 to 10, also tell him that. We're going to spend 4 hours. We're going to spend 2 hours doing a small iOS app that connects to Firebase, an online real-time database. And then we're going to do the same app in Android that connects to Firebase, an online real-time database. So you'll see two different types of mobile apps talking to a third-party database. So you'll kind of get a little crash course on the types of things your group might be dealing with at the hackathon. So if you're not interested, if you haven't seen that stuff before, you'll have at least a fighting chance. And at the same time, you'll also make sure that your tools are up to date on your laptop so that you're kind of ready for the hackathon. Sound good? All right, I'll see everybody on Tuesday.